Okay, so this is going to be the last video in Unit 3, and this is about Newton's third law of motion. And this is going to be a very short video, hopefully. So Newton's first law, just to recap, Newton's first law says that an object at rest remains at rest, and an object in motion remains in motion at constant velocity unless acted upon by a net force. Okay, Newton's second law says F net equals ma. The net force is equal to the mass of the object times its acceleration. Now, Newton's third law is another conceptual law. There's not usually any calculations with Newton's third law, but it's really important because it's responsible for things like, pushing off a wall and going backwards. It's responsible for, how rocket ships work, how airplanes work, gun recoil. Anytime you've ever experienced recoil, that is basically because of Newton's third law. We could not walk without Newton's third law, and so it's kind of important, in the real world. But it is a conceptual law. So here's what Newton's third law says: for every action, there is an equal and opposite reaction. Now, this is basically how everybody knows the third law, but you might think it's kind of strange because all the other laws don't talk about action, they talk about force. So really, what the third law, maybe it would be make more sense to say, would be for every force, there is an equal and opposite reaction force. Okay, and so basically for any push or any pull, there is automatically a reaction force to that push or pull. Okay, so in other words, forces always come in pairs, an action and a reaction. For every force from object A to object B, there is an equal and opposite force from object B to object A. Okay, equal meaning the same size, okay, opposite meaning in the opposite direction. And it's important that you understand that Newton's third law focuses on the force and reaction force between two objects. Because you might think to yourself at first, like, well, okay, so if every force has a reaction force and it's equal and opposite, shouldn't those two forces cancel out? Like, shouldn't it be like impossible for anything to move because the forces would always cancel out? And that's not actually true, because even though for every force there is an equal and opposite reaction force, those two forces act on two different objects. So for example, if you kick a soccer ball, your foot puts a force on the soccer ball puts the same force back on you. One of those forces is acting on the ball, the other force is acting on your foot. Okay, so equal and opposite forces, but they're acting between two different objects. So here are some really basic examples. Okay, you push on the wall. Your finger puts a force on the wall puts the same force back on your finger. If you push harder onto the wall, it's going to push harder back onto you, and you can feel that. Okay, that's because of Newton's third law. Okay, there's an action force. So in this case, the force from your finger on the wall is the action force. The reaction force would be the force from the wall on your finger. Okay, here's another example. A hammer hits a nail. Okay, the action force is the hammer puts a force on the nail. The reaction force is that the nail puts the same force back on the hammer in the opposite direction. Okay, equal and opposite, same size, opposite direction. But again, there's two objects here. There's always two objects with Newton's third law. Okay, in this case, the two objects are the hammer and the nail. Okay. One force is acting on the nail, the reaction force is acting on the hammer. Here's one more example. If you ever go swimming and you push off from the wall, okay, so that you go faster, your feet put a force on the wall. The wall puts the same force back on you, pushing you forward. Okay, that's why this girl, even though she is kicking and she's pushing her feet to the right, she's not going to move to the right, she's actually going to move to the left. Okay, because the force from the wall goes in the opposite direction, which pushes her to the left. Okay, so those are all situations involving Newton's third law. So again, this is mainly a concept law. You're not going to see a lot of calculations involving Newton's third law, but let's just do a few more examples. When you hit a nail with a hammer, the hammer puts a force of 50 newtons on the nail. What does Newton's third law say will happen as a result? Okay, so I'm just going to type this out. So the action force is the hammer puts a force of 50 newtons on the nail. Okay, so according to Newton's third law, the nail will put a force of negative 50 newtons back on the hammer. Now the negative sign here indicates direction. Okay, equal size, opposite direction. Okay, so that is example 1. Take a look at example 2. An ice skater pushes off from a wall. What does the third law say will happen? Well, we kind of talked about this already with the swimmer, but basically what's going to happen is the ice skater applies a force onto the wall. Because of the third law, the wall will apply an equal and opposite force on the ice skater. There you go. Okay, so Newton's third law, really simple problems, really simple to write, but really useful, like I said, because there's lots of applications that involve Newton's third law. Okay, so we'll just do a couple more really quick examples. Example 3. The Earth pulls down on Mr. Walker with a gravitational force of 1,000 newtons. What is the third law reaction force in this situation? When you're doing problems with the third law, you always need to identify the two objects involved, because there's always two objects with Newton's third law. Okay, so in this case, the two objects are Mr. Walker and the Earth. So let's write this out so we're really careful. Okay, so what is the action force? Well, it tells us that the action force is the Earth pulls Mr. Walker down with 1,000 newtons. Okay, the reaction force, remember with Newton's third law, the reaction force and the action force are always between the same two objects. That means the reaction force must be Mr. Walker pulls up on the Earth with 1,000 newtons. Now this example always blows people's mind. Everybody always asks me like, how can you pull up on the Earth? Like, you know, are you pulling on a string or something? No. Okay, your body has a gravitational force and the gravity of your body pulls up on the Earth. Now a lot of people are bothered by that. They say that doesn't make sense, but they're not at all confused by the fact that the Earth pulls you down. Okay, well, you have mass just like the Earth does, so your body is also capable of pulling the Earth up to you. Now, the Earth is so much bigger than you that you don't, notice the Earth move up, okay, but it does happen. Okay, the Earth pulls you down, you pull up on the Earth with the same force, and that is the force of gravity. Okay, that's kind of a really interesting example of Newton's third law. Okay, example 4. Identify how a rocket ship moves using Newton's third law. So I will just tell you the answer to this question, but basically it uses the principle of recoil. Okay, so recoil, you might know, is when you fire a gun and the gun goes backwards after you shoot it. And the reason the gun goes backwards is because when you shoot a gun, the gun puts a force on the bullet, right, making the bullet go out. The bullet puts an equal and opposite force backwards onto the gun. Okay, so the bullet goes one way, the gun goes back towards you. Okay, and that's how recoil works. So a rocket ship does not shoot out bullets. What a rocket ship does is a rocket ship actually shoots out what's called exhaust gas or high-speed gas particles. A rocket applies a downward force onto high-speed gas particles. Okay, just like if you've ever used a fire extinguisher, when you pull the handle, it shoots out gas particles out of the rubber nozzle. Rocket works in the exact same way, except it does it with way more gas particles, and they're much hotter because they're moving faster. Okay, a lot of people think there's fire coming out of the bottom of the rocket ship, but it's not really fire; it's just really hot gas, and there's a lot of it coming out. That's why it looks like it's glowing like fire, okay, but that's not what it is. So a rocket applies a downward force on the high-speed gas particles. Because of Newton's third law, the gas particles apply an equal force upward on the rocket, making the rocket go up. And so that's how a rocket ship works. Okay, rocket ship applies the downward force to the high-speed gas. Gas particles apply an equal and opposite force up on the rocket, making the rocket go in the opposite direction. Okay, so it's the exact same thing as recoil. Rocket applies the force one way, the recoil from that pushes the rocket in the opposite direction. A lot of people think rocket ships like push off of the ground, but it has nothing to do with pushing off of the ground. It has nothing to do with pushing off of the air. It's all about recoil, and that's how rocket ships can work in space, even if they don't have anything to push off of. Okay, so that is example 4. And then finally, example 5, a 1,000 kilogram cannon fires a 50 kilogram cannonball with a force of 25 newtons. Okay, now here we have some numbers, and there's 2 questions. First question says, which is greater, the force from the cannon on the cannonball or the force from the cannonball on the cannon? Okay, so think about that for a second. And if you've been paying attention to the last other like half a dozen examples, you should immediately recognize that because of the third law, the force on the cannon and the force on the cannonball are the same. Okay, they are the same force. Okay, now that does not mean they have the same outcome. That doesn't mean they do the same thing, but it means they have the same push on them. Okay, the cannon and the cannonball both have the same force on them. Just like when you shoot a gun, the bullet and the gun both have an equal and opposite force on each other, but the bullet flies that way faster. Why does the bullet fly out faster? Because it has less mass. Okay, so because of Newton's second law that says net force is equal to mass times acceleration, what that means is even if they have the same force, if one of them has a bigger mass, okay, the other one has to have a small, or whichever one has a bigger mass, that one must have a smaller acceleration in order to compensate. Okay, so the second question says which is greater, the acceleration of the cannonball or the acceleration of the cannon? In this case, it's definitely the acceleration of the cannonball because the cannonball has less mass. Look at the two masses, 1,000 kilograms for the cannon, 50 kilograms for the cannonball. Cannonball has the same force as the cannon, but because it has less mass, it has a bigger acceleration. Okay, because the forces have to be equal and opposite, but the accelerations do not. Okay, there's no law that says the accelerations are equal and opposite. It's only the forces that are equal and opposite. Okay, so like I said, Newton's third law is a really simple kind of concept type of deal. So don't expect a ton of calculations involving Newton's third law. Your practice assignment should be very straightforward and easy because there's not going to be a lot of calculations. But do make sure you understand that the forces come in pairs, action and reaction force, and the two forces act on two separate objects, which is why they don't cancel each other out. Okay, the forces are equal and opposite, but whichever object has a bigger mass is going to have a smaller acceleration and vice versa. So you should definitely now be able to solve problems involving Newton's third law. Please let me know if you have any questions, and as always, I will see you guys in the next video.